there exists a specific formula, an equation constructed from just 7 distinct variables that occupies a unique and unsettling space in the annals of scientific thought. It is not a precise equation in the traditional sense, one that describes the elegant, predictable motion of planets, the intricate and beautiful curvature of space-time, or the strange probabilistic behavior of a single quantum particle. This is an equation designed with a far grander and far more elusive purpose in mind. It is a piece of speculative mathematics that attempts to calculate a ghost to quantify a phantom. It is a line of simple algebra that endeavors to hold within its spare, elegant, and almost poetic framework the entirety of the grand and sweeping story of cosmic evolution, from the violent, fiery birth of the first stars to the quiet, emergent miracle of conscious thought. It was originally conceived in a spirit of pure, unbridled optimism, a structured and logical argument for a universe that should be teeming with vibrant life and ancient, wise intelligence. It was intended to be a mathematical roadmap, a clear and rational guide that would direct our nascent search for cosmic companionship and tell us where to look and what to expect. But over the long, silent decades of its existence, it has become something else entirely. It has slowly, inexorably transformed into an instrument of profound, of deep, and of unsettling silence. It is a formula that, in its most honest and unflinching modern application, seems to systematically and logically break the galaxy to drain it of all its expected and probable life, to expose our cosmic home as a vast, a beautiful, an ancient, and a haunted house. This is the detailed and cautionary story of the Drake equation, a simple, almost deceptive line of multiplicative algebra that promised to calculate the number of our celestial neighbors, but has instead become the single most powerful and chilling mathematical argument for why we are, to the best of our current and ever-improving knowledge, utterly, completely, and perhaps permanently alone. The equation is not merely a sterile string of abstract symbols, a cold and lifeless piece of mathematics. It is a narrative, a living story, a logical and chronological cascade that takes the user on a step-by-step journey through the greatest, the grandest, and the most mysterious story ever told. It begins in the incandescent, violent nurseries of the stars, the vast galactic clouds where suns and worlds are born. It then moves to the quiet, chemical-rich shores of nascent, watery planets, the potential cradles of biology. From there, it traces the improbable, the tangled, and the deeply contingent path of biological evolution, a 3 billion-year odyssey from a single self-replicating molecule to a complex thinking being. And it ends finally and perilously in the fragile, the brilliant, the powerful, and perhaps the tragically fleeting moment of a technological civilization, a species that has learned to speak in the language of electromagnetism and has thus made itself visible to the cosmos. Each of its 7 distinct and sequential variables is a gateway, a cosmic filter, a great and unforgiving hurdle through which the universe's immense and almost infinite potential for life must successfully pass. At each of these 7 gates, the staggering, almost incomprehensible numbers of the cosmos are methodically and relentlessly whittled down, the boundless possibilities are narrowed, and the cumulative odds of a final, successful, and detectable outcome shrink with every single solitary, multiplicative step. When the young radio astronomer Frank Drake first wrote his equation down on a blackboard in the year 1961, the numerical values of almost all of these variables were entirely and completely unknown. They were a collection of wild, educated guesses, of hopeful, optimistic speculations, and of profound acknowledged ignorance. In the 6 decades that have passed since that historic meeting, our global scientific enterprise has waged a relentless and astonishingly successful campaign against that foundational ignorance. We have, with our powerful new telescopes, our deep space probes, and our advanced supercomputers, filled in many of the crucial blanks. We have systematically and triumphantly replaced pure speculation with hard observational data. We have sharpened the once fuzzy, ambiguous edges of our cosmic vision into a clear and high-resolution picture of our place in the universe. And with every new piece of hard-won knowledge, with every one of the 5,000 new exoplanets discovered, with every new and profound insight into the complex and contingent nature of life and of intelligence, the equation's final, stark, and deeply paradoxical conclusion has only grown more powerful, more insistent, and more scientifically terrifying. It has become the precise mathematical formalization of the great cosmic silence. It is a formula that does not, as was once hoped, resolve the deep mystery of our solitude, but instead, it exposes that solitude in its full, its stark, its statistical, and its almost unbearable clarity. It has become the equation that tells us not how many aliens are waiting to be found, but why the vast star-dusted sky is so terrifyingly, so unnaturally, so profoundly, and so completely quiet. The intellectual seeds of this strange, powerful, and ultimately haunting formula were sown not in the quiet, dusty stacks of a university library or in the contemplative solitude of an astronomer's office, but in the brilliant, the sun-drenched, the highly secured, and the deeply paranoid atmosphere of the Los Alamos National Laboratory in the long, hot summer of the year 1950. It was there during a casual, collegial, and now legendary lunchtime conversation about the recent nationwide craze of flying saucer sightings that the brilliant Italian physicist Enrico Fermi first posed the deceptively simple question: would ignite and define the entire paradox. Struck with a sudden intuitive insight by the simple glaring contradiction between the high statistical probability of alien life and the complete and utter lack of any concrete physical evidence for its existence, he turned to his physicist colleagues and asked a simple, a devastating, and a now immortal question: where is everybody? This was not, it must be understood, the beginning of the search for extraterrestrial life. It was in a very real sense the beginning of the doubt. It was the first formal and public recognition of the great silence, not as a temporary and solvable problem of our limited technology, but as a deep, fundamental, and a profoundly disturbing mystery about the very nature of the universe and the destiny of intelligent life within it. Enrico Fermi's question was a lightning flash of intuitive, quantitative genius, a rapid back-of-the-napkin calculation that revealed a profound and troubling inconsistency at the very heart of our most basic and optimistic cosmic assumptions. For a full decade, his disquieting question remained a piece of esoteric intellectual folklore, a chilling and compelling little riddle that was whispered and debated among the elite insular communities of physicists and engineers who were then designing the nuclear arsenal of the Cold War. It was not until the year 1961 that a young, brilliant, and deeply optimistic radio astronomer named Frank Drake took the next decisive and historic step. He was tasked with the seemingly simple job of setting the scientific agenda for the first ever formal conference on the search for extraterrestrial intelligence, SETI, a small and groundbreaking meeting to be held at the National Radio Astronomy Observatory in Greenbank, West Virginia. Drake, seeking a logical and systematic way to structure the conference's discussion, wanted to break down the single, overwhelming, and almost unmanageable question of "are we alone?" into a clear and logical series of smaller, more manageable, and, most importantly, potentially answerable scientific questions. In a few quiet hours of focused contemplation before the conference, he took a piece of paper and wrote down the now famous equation. In a stroke of brilliant clarity, he took the grand sweeping and informal logic of Enrico Fermi's intuitive thought experiment and gave it a formal, a rigorous, and an elegant mathematical skeleton. He created a simple, a powerful, and a beautiful machine for thinking, a conceptual tool designed not for the arrogant purpose of producing a final definitive answer, but for the humble and far more useful purpose of organizing our vast and multi-layered ignorance. With his 7 variables, he laid out the 7 great hurdles, the 7 distinct and sequential cosmic gates, through which any potential communicative civilization must successfully pass in order to exist and to be detectable by us. He gave us for the very first time a common quantitative language to speak about the myriad contingent probabilities of our own seemingly miraculous existence. The Drake equation was the embodiment of Frank Drake's personal dream, a dream of a rational, a patient, and a systematic scientific search, a clear and logical way to turn the loudest, the most emotionally charged, and the most philosophically loaded of all human questions into a quiet, a sober, and a methodical scientific pursuit. But in the very act of formalizing Enrico Fermi's dark and cautionary napkin math, he had unknowingly and unintentionally created something far more powerful, far more ambiguous, and far more unsettling than he had ever intended. He had created a prophecy machine, an engine of pure logic, that when fed with our best, our most honest, and our most current scientific knowledge of the cosmos, produces a result that makes the fine hairs on the back of our necks stand up. It is a formula that takes the almost infinite star-dusted promise of the cosmos and step by painful, inexorable, and logical step, reduces it down to a stark, to a lonely, and an insignificant integer, or worse, far worse, to a desolate, barren, and an unforgiving 0. It is a formula that was designed by a hopeful optimist to help us find our friends in the great dark void. It has instead, over 60 years of hard-won scientific progress, become the single most powerful and compelling argument for why we have no friends at all. It is the equation that logically and systematically broke the galaxy, and in the very process of doing so, it has forced us with an uncomfortable and insistent pressure to confront the most difficult, the most important, and the most deeply personal question. Of all, are we, ourselves, the final, the impossible, the miraculous, and perhaps the most terrifying variable in the entire grand, silent, and cosmic calculation? The enduring power of the Drake equation lies in its deceptive and beautiful simplicity. It is at its heart a simple multiplicative chain of 7 distinct and independent links, a carefully ordered sequence of probabilities that must be multiplied together one after the other to arrive at a final single number. That number, designated by the letter n, represents the calculated best guess estimate for the number of currently active, technologically advanced, and actively communicative civilizations in our home galaxy, the Milky Way. To work through the equation is to take a journey, a chronological and logical progression that mirrors the great cosmic story of creation itself. At each of the 7 steps, we are forced to confront a deep and fundamental question about the nature of the universe. The very first variable, denoted as R star, can be thought of as the galaxy's fundamental heartbeat, the steady, rhythmic, and creative pulse of its ongoing creation. It represents the average net rate of star formation in our galaxy, the specific speed at which the vast, the cold, and the dark clouds of interstellar hydrogen and molecular dust slowly and patiently collapse under the gentle, persistent force of their own weight to ignite as brilliant, new, and life-giving suns. This first foundational number sets the grand initial scale of the entire problem. It tells us the sheer, almost unimaginable number of new opportunities for life, the total number of new solar systems being born each and every year, each one a brand new, pristine, and potential stage upon which the great and mysterious drama of life and intelligence might one day possibly unfold. The next 2 variables in the chain, FP and NE, are the great astronomical filters. They are the variables that bring the grand cosmic focus down from the general undifferentiated population of stars to the very specific and much rarer subset of worlds that might one day be called home. The variable Fp represents the fraction of those newly formed stars that are orbited by planets. For almost the entirety of human history, this number was a complete and total unknown, a matter of pure, untestable, philosophical speculation and imaginative science fiction. We simply did not know if our own solar system, with its rich and diverse retinue of worlds, was a common and typical arrangement in the cosmos, or if it was a bizarre, a precious, and a lonely fluke. The next variable, Ne, narrows the focus even further and with a much greater degree of selectivity. It represents the average number of planets per star that has a planetary system that are actually suitable for the origin and the long-term sustenance of life as we know it. This is the now famous Goldilocks variable, the specific number of worlds in a given system that are not too hot and not too cold, not too large and gaseous and not too small and airless, but are in fact just right. This is the number of worlds with a stable near-circular orbit, a solid rocky surface, and most critically, the long-term potential for vast quantities of liquid water. These two purely astronomical variables, when multiplied together, take us from the raw, almost infinite number of stars in the galaxy to the much smaller, but still potentially vast number of habitable Earth-like worlds. They define with a growing and data-driven precision the total number of potential cradles for life that our galaxy has to offer. With the next two deeply mysterious variables, Fl and Fi, we must leave the relatively firm and comfortable ground of observational astronomy and take a bold and uncertain step into the deep, the murky and the treacherous waters of theoretical biology and evolutionary theory. These are the great biological filters, and they represent the single greatest, most profound, and most significant leap of scientific faith in the entire logical structure of the equation. The variable Fl represents the fraction of those suitable, habitable, and water-rich planets on which life actually spontaneously and against all the odds of entropy emerges from simple, non-living chemistry. It is the variable of abiogenesis, the deep and enduring mystery of the first spark of life. It asks a question that our current science is not yet and may never be fully equipped to answer: is life a cosmic imperative, a natural, a robust, and a common outcome of the fundamental laws of planetary chemistry and thermodynamics? Or is it a 1 in a trillion, a 1 in a quintillion chemical fluke, a lottery win of such staggering and monumental odds that it may have in fact happened only once in the entire observable universe? The next variable, Fi, is the equally profound and perhaps even more controversial filter of intelligence. It asks a very different but no less difficult question of all the countless worlds where simple microbial life has successfully taken root and flourished. On what tiny fraction of them does it, eventually over the course of billions of years of chaotic and contingent evolution, give rise to a species with what we would recognize as a high level of intelligence? This is the filter of consciousness, of abstract thought, of complex tool use of symbolic language, a single, lonely, evolutionary hurdle that, on our own planet, took more than 3.5 billion years of trial and error to successfully cross, and whose successful and unlikely navigation was by no means a guaranteed or a predictable outcome: the evolutionary process. The final two variables in this long and perilous chain, Fc and L, are perhaps the most chilling, the most unsettling, and the most deeply personal of all, for they are not about the impersonal laws of physics or the blind processes of biology. They are about us. They are the great and terrible sociological filters. The variable F10C represents the fraction of those rare intelligent species that go on to develop a technology that is powerful enough and loud enough to be detectable from the vast and silent distances of interstellar space. This is the filter of curiosity, of science, of ambition, and perhaps even of a certain kind of aggressive, outward-looking psychology. A peaceful and deeply spiritual civilization of brilliant aquatic cetacean philosophers, or a stable, ancient and deeply conservative society of tree-dwelling arboreal poets would be completely and permanently invisible to our radio telescopes, their profound intelligence and their rich culture, forever trapped and hidden beneath the waves or the canopy of their home world. But it is the seventh, the final, and the dreaded and all-important variable, the single letter L, that is the true, the beating, and the potentially blood-soaked heart of the entire Fermi paradox. The variable L represents the average mean lifetime of a technological civilization, the specific length of time during which it remains active, powerful, and electromagnetically detectable. This is not a variable about origins, it is a variable about endings. It asks the darkest, the most profound, and the most relevant question of all. Once a species becomes intelligent and powerful enough to be heard across the vast, silent gulfs between the stars, how long does it typically last before it falls? Permanently silent, either through a sudden act of violent self-destruction, through a slow and quiet process of technological transcendence and withdrawal from the physical world, or through some other unforeseen and perhaps unimaginable catastrophe. This is the variable that contains the very essence of Enrico Fermi's dark and hidden warning. These, then, are the seven deadly variables, the seven great sequential gates of cosmic probability and contingency. To solve the Drake equation is to attempt to assign a reasonable, a plausible, and a scientifically defensible value to each one of these seven distinct and challenging terms, from the astronomically vast numbers of the cosmos to the infinitesimally small probabilities of biology and sociology, and then to multiply them all together in a single, final, and sobering calculation. The result, the single stark number n, represents our best, our most honest, and our most informed guess as to the current population of our great galactic city. When Frank Drake and his optimistic colleagues first played with the numbers of the equation in the hopeful, heady days of 1961, their confident and cheerful estimates for each variable produced a galaxy that was teeming with thousands or even millions of intelligent, communicative civilizations. They envisioned a vibrant, a noisy, a crowded, and a deeply interesting cosmos. But as our scientific knowledge has grown over the subsequent 6 decades, as our deep and humbling understanding of the profound and almost miraculous difficulties at each and every step of this long process has sharpened, the final, calculated number has begun to shrink, to dwindle, to collapse. The Drake equation has slowly, and with a terrible tragic irony, transformed from a bright beacon of scientific hope into a cold, dark machine for generating silence. It is a step-by-step, logical and unavoidable journey that takes the glorious, the beautiful, and the star-filled promise of our night sky and systematically, ruthlessly exposes it as a beautiful, a profound, and perhaps a terrifying illusion. Each of the 7 variables is a slow, inexorable turn of the screw, tightening the logic of the paradox until we are left at the end of the calculation, completely and utterly alone in the vast, echoing quiet, wondering with a new and desperate urgency which of these 7 deadly gates was the one that slammed shut for everyone else, and which one we ourselves in our own fragile and deeply uncertain time are currently and perhaps irrevocably approaching. The grand cosmic journey of the Drake equation begins with a number of almost spiritual, almost mythical grandeur, a powerful and humbling testament to the ceaseless creative and generative power of the cosmos. The first and most foundational variable, R star, the average rate of formation of stars that are suitable for the potential development of intelligent life sets the magnificent and almost boundless stage for the entire subsequent drama. Our galaxy, we now know, is not a static, unchanging museum of ancient and dying suns. It is a dynamic, a vibrant, and a living entity, a vast, churning and self-regulating engine of cosmic creation. In the great, the cold, the dark, and the beautiful clouds of interstellar gas and dust, the vast and serene stellar nurseries, the gentle but inexorable force of gravity is patiently, silently, and constantly at work. Over the course of millions of years, it slowly and delicately pulls the diffuse cold hydrogen together, spinning it into dense, hot, and ever more compact cores. When the immense pressure and the searing temperature at the very center of these collapsing primordial knots of matter finally reach a critical thermonuclear threshold, a new star is born, a stable, long-lived, and life-giving furnace that will shine with a steady and nurturing light for billions or even trillions of years. Our modern multi-wavelength astronomical surveys are breathtaking deep-field images that capture the faint ancient light of the very first galaxies, and our detailed high-resolution radio maps of the cold, dark hydrogen clouds in our own Milky Way have given us a firm, a confident, and a data-driven handle on this crucial initial number. We now know, with a high degree of certainty, that our home galaxy in its current mature and stable state produces, on average, about 3 new sun-like stars every single year. This number 3 stars per year may at first seem deceptively and unimpressively small, but the true awesome power of the Drake equation lies in its deep time perspective, its ability to integrate over the vast, almost unimaginable sweep of cosmic history. We are not just concerned with the handful of stars that are being born today, but with the colossal and almost uncountable number of stars that have ever been born over the galaxy's immense 13 billion year history. The total number of sun-like stars that currently exist, or have existed at some point in the past in the Milky Way, is a number so vast that it dwarfs all human scales of comprehension and reduces our terrestrial concerns to a state of near insignificance. The conservative estimate of 100 billion stars is now known to be just the beginning. The true number is likely closer to 400 billion. Let us pause for a moment to truly feel the profound and humbling weight of that number. For every single human being that has ever lived and died on this planet, from our earliest struggling ancestors to the present day, there are at least 50 stars shining brightly in our home galaxy. For every single tiny grain of sand on every beach, in every desert, on the entire surface of the Earth, there is a star, a sun, burning in the depths of the Milky Way. This is the raw, the untamed, the almost infinite potential that the universe provides as its starting condition. The very first variable in the Drake equation is not a filter. It is a great and roaring floodgate, a powerful and undeniable declaration of cosmic abundance and of boundless creative potential. It tells us with a mathematical certainty that the universe is not stingy or parsimonious with its opportunities. It has built a vast and beautiful celestial city of at least 100 billion suns, 100 billion potential campfires, around which a young and hopeful civilization might one day possibly gather to warm itself and to tell its stories. The stage is set, and it is almost unimaginably, almost terrifyingly vast. The second and third variables in the Drake equation, Fp and Ne, are the points in our logical journey where we begin to methodically narrow our search from the vast general population of all stars to the much more specific, much rarer, and much more interesting subset of worlds that might with a great deal of luck be called home. For almost the entirety of human history, the numerical values of these two crucial variables were a complete and total mystery. the exclusive province of philosophical debate, of religious speculation, and of imaginative science fiction, dreams. We knew of only one planetary system, our own, and we had absolutely no way of knowing if its familiar and comfortable arrangement was a cosmic standard, a common and predictable outcome of star formation, or if it was in fact a bizarre, precious, and a deeply lonely fluke of nature. The last 3 decades of astronomical research, however, have witnessed a quiet and profound revolution in our knowledge, a revolution that is arguably the most significant and the most transformative in the entire long history of astronomy. The brilliant and painstaking development of incredibly precise new observational techniques, the delicate and patient transit method which detects the tiny dimming of a star as a planet passes in front of it, and the subtle wobbling radial velocity method which detects the tiny gravitational tug of a planet on its parent star, and most importantly, the design, the launch, and the spectacularly successful operation of dedicated space-based planet-hunting observatories like NASA's Kepler Space Telescope and its successor, the Transiting Exoplanet Survey Satellite, TESS, have completely, irrevocably, and triumphantly transformed our fundamental understanding of our place in the cosmos. The variable FP, the simple fraction of stars that have planets, has, for all intents and purposes, been definitively and triumphantly solved. The answer, an answer that would have stunned and perhaps even frightened the astronomers of Enrico Fermi's generation, is approximately 1. That is to say, our vast and ever-growing body of observational data now strongly and with an increasing statistical certainty indicates that virtually every single star in our night sky has at least one planet, and that most of them, like our own Sun, have a whole rich and diverse system of them. Planets, we have discovered, are not a rare and precious byproduct of the messy process of star formation. They are a ubiquitous, an integral, and an inevitable part of it. The galaxy is not, as was once thought, a collection of lonely, isolated, and childless stars. It is a vast and teeming collection of 100 billion distinct and unique solar systems. This single hard-won scientific discovery, made entirely within the lifetimes of many of us alive today, has profoundly and permanently transformed the cosmos from a potentially empty and sterile void into a place of almost infinite, boundless possibility. Every single tiny point of light in our night sky is no longer just a distant burning ball of gas. It is now a potential destination. It is a potential home. With the next variable ni, we sharpen our focus even further, moving from the general to the specific with the precision of a surgeon's scalpel. Of these countless, now proven trillions of planets in our galaxy, how many are actually truly suitable for the origin and the long-term sustenance of life as we currently understand it? How many of these worlds are privileged, lucky members of the exclusive and highly sought-after Habitable Zone Club? This is the patient and ongoing search for Earth's true twins for rocky terrestrial worlds of a similar size, a similar mass, and a similar composition to own. Worlds that orbit their parent star at that perfect, that delicate, and that life-giving Goldilocks distance. And this is where the modern astronomical data becomes truly almost unbelievably breathtaking. The great digital fire hose of information that has poured down from the Kepler mission over the last decade has allowed us for the first time in history to perform the first real statistically significant census of the different types of planets that exist in our local galactic neighborhood. The current and still deliberately conservative estimates, which have been carefully extrapolated from the many thousands of confirmed exoplanets that we have found and characterized, suggest that roughly 1 in every 5 sun-like stars in the Milky Way hosts a rocky Earth-sized planet orbiting within its habitable zone. Let us for a moment pause and run those staggering numbers. If we take our deliberately conservative starting estimate of 20 billion sun-like stars in the Milky Way, and we multiply it by this new hard-won and data-driven estimate of 1 in 5, we arrive at a final, almost incomprehensible number of 4 billion. 4 billion Earth-like, potentially habitable, and potentially water-rich worlds. This is not science fiction. This is not a hopeful guess. This is the direct, the sober, the almost unbelievable, but the scientifically unavoidable conclusion of our best, our most powerful, and our most current astronomical observations. Our galaxy is not a barren, sterile desert with a single lonely and miraculous oasis. It appears to the best of our current knowledge to be a lush, a vibrant, and a tropical jungle, a cosmic greenhouse that is filled with a staggering and almost embarrassing number of worlds that possess all of the fundamental raw and necessary ingredients for the emergence of life. The first 3 purely astronomical variables of the Drake equation, the great and once unknown filters of stars, of planets, and of homes, have turned out to be far less exclusive, far more generous, and far more optimistic than anyone, even in their wildest dreams, had ever dared to hope. They have painted a clear and stunning picture of a cosmos that is not just ready for life, that is not just waiting patiently for life, but is practically almost desperately begging for it to begin. Our galaxy, it seems, has prepared a great and bountiful feast of 4 billion perfect, pristine, and water-friendly worlds. The great, the terrible, and the enduring question that remains is, has anyone, anywhere in the last 13 billion years ever come to the table? With the 4th and deeply mysterious variable FL, we arrive at the first of the great and terrible filters in the Drake equation, a sheer dark wall of profound and almost total uncertainty, a wall so high and so thick that it threatens to halt our entire logical journey before it has even truly begun. We have, with a growing and data-driven confidence, established that our home galaxy is filled with a staggering and almost uncountable number of suitable Earth-like and potentially habitable worlds. The raw chemical materials are in place. The physical and environmental conditions are in billions of cases just right. But what we must ask is the actual numerical probability that life will ever actually emerge on any one of these billions of perfect, pristine planets. This is the great and enduring question of abiogenesis, the deep, the dark, the profoundly complex, and the still almost completely unsolved scientific mystery of the origin of life from simple non-living matter. It is at this precise point in our calculation that we must reluctantly leave the confident, the data-rich, and the well-trodden realm of modern astronomy and venture out into a strange, a new, and a deeply unfamiliar world of laboratory chemistry, of theoretical speculative biology, and of deep, unresolved, and perhaps unresolvable philosophical debate. On one side of this great and ongoing scientific debate are the eternal optimists, the proponents of a powerful and compelling theory that is known as biochemical determinism. They argue with a growing body of circumstantial evidence that the emergence of life is not a random lucky fluke, but is in fact a cosmic imperative, a natural and almost inevitable outcome of the fundamental laws of physics, chemistry. The laws of chemistry and thermodynamics, they contend, are not random or chaotic. They have a built-in, an inherent, and a powerful tendency to create ever-increasing levels of complexity, to self-organize, and to form stable information-rich structures. In the warm, the shallow, and the chemical-rich waters of a primordial Earth-like planet, a planetary-scale laboratory that is constantly being bombarded by the raw, energetic radiation of its young and active sun and the powerful electrical discharges of its turbulent, lightning-filled atmosphere, the spontaneous emergence of complex self-replicating molecules is not just a remote possibility, it is over the patient grinding timescales of geology, an almost certain and inevitable event. The universe in this optimistic and beautiful view is fundamentally and beautifully hardwired for life. The supporters of this hopeful idea point with a great deal of justification to the astonishing and almost shocking speed with which life appeared on our own planet. The Earth first formed from the solar nebula around 4.5 billion years ago, and for its first few 100 million years, it was a molten, a violent, and a completely inhospitable hellscape, a world that was constantly and brutally being bombarded by a rain of giant ocean-vaporizing asteroids and comets. And yet, the very moment that the planet had cooled enough for liquid water to form and to remain stable on its surface, the first clear and unambiguous fossil evidence of simple single-celled microbial life appears almost instantly and robustly in the geological record around 3.8 billion years ago. This undeniable chronological fact strongly suggests that the great and mysterious transition from a sterile, primordial chemical soup to a living, a breathing, and a thriving biosphere was not a long, a drawn-out, a difficult, and a highly improbable process, but was in fact a quick, a robust, and perhaps even a chemically easy one. If it happened that fast, that easily, and that robustly here, the optimists argue with a powerful logic, then it must be happening on countless other similar worlds all across the galaxy. For them, the numerical value of the variable FL is very, very close to 1. But on the other side of this great unresolved debate are the scientific pessimists, and their dark cautionary and equally compelling arguments cannot be so easily dismissed. They argue with a cold and rigorous logic that we as a species are suffering from a profound, an unavoidable, and a potentially deeply misleading observational bias. We are alive, and therefore we must, by simple and tautological definition, find ourselves existing on a planet where the unlikely event of abiogenesis successfully occurred. This simple fact, they argue, tells us absolutely nothing about how probable that event actually was in a cosmic context. It could be, for all we know, that the specific complex and highly contingent sequence of chemical reactions required to form the very first stable information-carrying and self-replicating molecule, something like a primitive RNA, strand is a lottery of such, stupendous of such, astronomical, and of such almost unimaginable odds that it has in all of cosmic history, in fact happened only once, right here, on our own small and uniquely fortunate world. The total combinatorial number of possible stable but non-living chemical arrangements of matter on a planetary surface is for all practical purposes infinite. The tiny, specific and privileged number of those combinations that successfully lead to the emergence of life may be vanishingly, heartbreakingly, and immeasurably small. To confidently and optimistically assume that life is a common and inevitable phenomenon just because it happens to exist, here is, the pessimists argue, a profound and dangerous logical fallacy, a mistake as simple and as arrogant as a lottery winner who assumes on the basis of their own singular good fortune that winning the lottery is an easy and a common event for everyone. The pessimists argue that we simply do not, and perhaps cannot know the true probability of this singular event, and to assume that it is high is not a scientific conclusion, but is an act of blind, unscientific, and perhaps deeply misguided faith. For them, the numerical value of FL could be a number so vanishingly, so infinitesimally close to zero that it effectively and single-handedly reduces the final calculated answer of the Drake equation to zero all by itself. Abiogenesis, in this view, is not a simple low hurdle that is easily cleared by any suitable world. It is a sheer, a smooth and 1,000-mile high cliff face of pure statistical improbability. and we may be the only ones in the entire vast history of our galaxy who have ever, by some miracle of pure dumb luck, managed to scale it. This is the great and unresolved abiogenesis lottery, and the stark, the sober, and the humbling truth is we have no idea if we are holding a winning ticket from a game that is played on every street corner of the cosmos, or if we are the sole, the lonely, and the miraculous holders of the one and only winning ticket from a grand cosmic game that is played only once in a universal eternity. But let us, for the sake of continuing our perilous logical journey, and in a spirit of cautious and provisional optimism, assume for a moment that the optimists are right. Let us assume that life itself is a common and robust cosmic phenomenon, that the galaxy is teeming with 1 billion worlds that are covered in a rich, a diverse, and a beautiful microbial slime. This hopeful assumption immediately brings us face to face with the next and perhaps even more formidable of the great biological filters, the variable Fi, the specific and tiny fraction of those life-bearing worlds on which a high level of intelligence and eventually a technological civilization evolves. Even if a planet is completely and thoroughly covered in simple, thriving life, what is the actual numerical probability that this life will, over the course of billions of years of random mutation and natural selection, eventually evolve into a species with a high degree of consciousness, with the capacity for abstract thought, with the ability to manufacture and to use complex tools, and with the unique and perhaps strange desire to understand and to manipulate its environment in complex and profound ways? The long and bloody history of our own planet offers a deeply sobering, a deeply humbling, and a profoundly cautionary perspective on this crucial and difficult question. Life in its simplest microbial form has existed on our planet Earth for at least 3.8 billion years. For the first 3 billion of those years, for the vast, the overwhelming, and the almost unimaginable majority of life's entire history on this planet, it remained exclusively and stubbornly at the level of simple, solitary, and unintelligent, single-celled organisms like bacteria and archaea. The great, the revolutionary, and the still poorly understood evolutionary leap to complex multicellular life was an incredibly difficult, a highly contingent, and a perhaps very rare event in the history of our world. And the subsequent, even more difficult evolution of a large, a metabolically expensive, and a dangerously fragile brain was another, even more unlikely and even more recent evolutionary development. The long and successful reign of the dinosaurs serves as the great, the powerful, and the definitive cautionary tale in this particular chapter of our cosmic story. They were the undisputed, the unchallenged, and the globally dominant form of complex vertebrate life on this planet for over 160 million years. That is a reign of evolutionary success, of ecological stability, and of sheer temporal endurance that is almost beyond our limited human comprehension. Our own species has existed for a mere 300,000 years, and our technological civilization for less than 10,000. And in all of that immense 160 million year stretch of time, in all of those countless successive generations of magnificent creatures, not a single one of their thousands of diverse and successful species ever showed the slightest, the faintest inclination towards developing what we, in our arrogant and self-serving way, would call technological intelligence. They were magnificent, they were powerful, they were successful, and they were perfectly and beautifully adapted to their prehistoric world, but they never once in all that time learned to control fire. They never once in all that time deliberately chipped a piece of flint to make a stone tool. And they never once in all that time looked up at the moon and the stars and wondered with a scientific curiosity if anyone or anything was looking back at them. They never built a radio telescope. The giant asteroid that so violently and so abruptly wiped them from the face of the Earth some 66 million years ago was a random, a contingent, and a purely accidental event. If that single 6-mile-wide piece of rock had happened to miss our planet, if its trajectory had been off by just a few thousand miles, it is entirely possible, and perhaps even overwhelmingly probable, that the planet Earth would still to this very day be a planet of magnificent, of beautiful, of successful, but of completely non-technological reptiles. This is the famous and powerful argument from the late great paleontologist and evolutionary biologist Stephen Jay Gould, who argued with a passionate and compelling logic that if you were to somehow rerun the tape of life on Earth, you were to start the whole chaotic, messy process of evolution over again, from the very beginning. The chance of something even remotely like human technological intelligence emerging again is vanishingly, almost infinitesimally small. Intelligence in our specific, our strange, and our perhaps deeply pathological technological form may not be a common, a predictable, or a convergent goal of the evolutionary process. It may in fact be a strange, a recent, a bizarre, and a perhaps deeply unstable and maladaptive evolutionary experiment. The galaxy could at this very moment be filled with 1 billion worlds that are teeming with rich and complex life, with vibrant alien jungles and with vast, deep and teeming alien oceans, worlds of breathtaking, unimaginable biological beauty and diversity, but worlds that are and will forever remain utterly and completely silent to our searching radio telescopes. A global and deeply ancient civilization of brilliant, sentient and philosophical trees, or a stable and harmonious underwater society of intelligent, poetic, and non-manipulative dolphins would leave no detectable technological mark on the wider cosmos. The specific and highly contingent evolution of a species precisely like our own, a species with delicate grasping and tool-making, hands with complex and language-capable vocal cords, and with an insatiable, a relentless and perhaps even a uniquely pathological curiosity about the nature of the universe, may be another profound and almost miraculous evolutionary rarity. The great and perhaps final biological filter of intelligence strongly suggests that a living world does not by any means necessarily become a thinking world. The long, the difficult and the treacherous journey from a simple microbe to a complex technological mind may be the hardest, the rarest and the most perilous journey of all. We have now, in our long and difficult logical journey, crossed the great, the wide and the uncertain chasms of biology and of evolution, and we finally arrive at the last two, and in many ways the most human of the variables in the Drake equation. These are the great and terrible sociological filters, the variables that are not about the impersonal and universal laws of the cosmos, but are about the specific, the contingent, and the deeply mysterious nature of civilizations themselves. It is here in this final section of the equation that the great cosmic calculation becomes a dark and an unforgiving mirror, a reflective surface that forces us to turn our gaze away from the distant stars and to look with a new and of terrible honesty at the deepest, the darkest, and the most difficult questions about our own young and deeply troubled species, and about our own fragile and deeply uncertain future. The first of these two final variables, denoted as FC, represents the fraction of those rare intelligent species that actually go on to develop a technology that is powerful enough, that is loud enough, and that is persistent enough to be capable of being detected across the vast and silent distances of interstellar void. This might at first glance seem like a small, a trivial, and an almost automatic step in the process. Once a species has achieved a high level of intelligence, does it not by a process of inevitable and logical progression develop science, and then technology, and then communication? The answer upon closer inspection is not necessarily. An intelligent species could, for example, have a collective psychology that is fundamentally non-inquisitive, or is deeply and spiritually opposed to the aggressive, and often destructive manipulation of its natural environment. It could live on a world like a planet completely covered by a deep global ocean or a gas giant, with no solid surface, where the crucial early steps of technological development like the control of fire and the smelting of metals and the development of complex electronics are physically and permanently impossible. It could develop a stable, a harmonious, a sustainable, and a deeply philosophical culture that has no interest whatsoever in the aggressive, the expansionist, and the often self-destructive path of relentless technological development. The powerful and almost universal impulse to build radio telescopes, to deliberately and loudly shout into the vast cosmic void, to try and leave one's planetary cradle, and to travel to the stars, may be a very rare, a very strange, and a perhaps uniquely human form of ambition, of hubris, and of deep existential loneliness. The silent galaxy could at this very moment be home to 1,000 distinct and ancient civilizations of brilliant poets, of wise mystics, and of contented philosophers living in quiet, sustainable, and harmonious contemplation, their profound and beautiful intelligence completely and forever invisible to our searching and perhaps overly aggressive technological gaze. But it is the seventh, the final, the single-lettered and the great and terrible variable L that is the true, the beating, the dark, and the potentially blood-soaked heart of the entire 60-year-old Fermi paradox. The variable L represents the average mean lifetime of a technological civilization, the specific and measurable length of time that it remains active, that it remains powerful, and most importantly, that it remains electromagnetically detectable before it finally, and for whatever reason, falls permanently and irretrievably silent. This is the great and terrible trap that lies hidden in the simple, elegant mathematics of the Drake equation, the very singular act of developing the specific and powerful technology that is required to be counted in the equation in the first place, the technology of powerful radio astronomy, of rocketry, and of spaceflight, of massive planetary-scale energy generation, may be inextricably, fatally, and universally linked to the simultaneous and unavoidable development of a whole suite of other equally powerful technologies that lead with an almost mathematical certainty to a civilization's own swift and certain demise. This is the very essence of Enrico Fermi's dark, hidden, and deeply personal warning, now made explicit and quantifiable in the final term of the equation. The rapid and exponential acquisition of great godlike technological power is not necessarily, and perhaps is not even likely to be, correlated with the slow, difficult, and painful acquisition of great collective and global wisdom. In fact, the bloody and chaotic evidence from our own brief human history suggests quite the opposite. We as a species first developed the crude but effective ability to send powerful and coherent radio signals into space in the early years of the 20th century. Just a few short and violent decades later, in the 1940s, we developed the terrifying and absolute ability to destroy ourselves and our entire world with the awesome and terrible power of nuclear weapons. Our window of potential cosmic detectability and our window of potential total self-annihilation opened at almost exactly the same fraught and perilous historical moment. What then is a plausible, a reasonable, and a scientifically defensible value for the great and terrible variable L? If we are to be true optimists, if we are to have a deep and abiding faith in the ultimate wisdom of intelligent life, might imagine a typical civilization that successfully and wisely navigates the treacherous and turbulent waters of its own technological adolescence. We can imagine a civilization that solves its internal tribal conflicts, that abolishes war, that achieves a state of sustainable, of peaceful, and of enlightened global cooperation, and that then goes on to live and to thrive for millions, even for billions of years. In this beautiful and hopeful scenario, the value of L would be a very, very large number, and the galaxy, as a direct and unavoidable consequence, should be filled to the brim with these ancient, these stable, these wise, and these easily detectable super-civilizations. But what if this beautiful, optimistic scenario is the naive, the foolish, and the vanishingly rare exception, and not the common, brutal, and universal rule? What if the average, the typical lifetime of a technological civilization is only a few hundred or a few thousand short and violent years? What if every single species that reaches our own precarious level of technological capability inevitably and universally succumbs to the dark, seductive, and siren song of its own most powerful and most terrible weapons, or carelessly and short-sightedly poisons its own fragile biosphere, or arrogantly and foolishly unleashes an artificial intelligence that it cannot in the end control? In this dark and deeply pessimistic case, the value of L would be a devastatingly, a tragically, and a crushingly small number. Civilizations in this view would be like ephemeral summer fireflies in the great dark cosmic night, blinking brightly into existence for a brief, a brilliant and a beautiful moment, and then extinguishing themselves silently and forever. The galaxy could have hosted 1 billion such brilliant and tragic civilizations over its long and patient history, but at any given single moment in time, the number of them that are active and alive would be vanishingly, almost immeasurably small, separated from each other by immense, unbridgeable gulfs of both empty space and of silent, deep time. This is the great and inescapable L factor trap. It suggests with a cold and brutal logic that the ultimate reason the sky is so quiet, so silent, so empty, is that the period of noisy, of expansive, and of detectable technological activity is an inherently, a universally, and a deeply unstable, transient and tragically brief phase in the life of any intelligent species. The profound and enduring silence that we observe with our telescopes is the direct, the empirical, and the undeniable sound of this great final filter at work, a filter that has closed with a grim, a silent, and a final finality on countless brilliant and hopeful civilizations before us. And in this final, terrible realization, the Drake equation transforms from a simple academic census of our potential cosmic neighbors into a chilling and deeply personal calculation of our own specific and deeply uncertain odds of long-term survival. The true value of L is not a distant, an abstract, or an astronomical number that we can ever hope to measure by looking at the stars. It is a number that we and we alone in our own small corner of the cosmos are in the very process of determining for ourselves with every single collective choice we make every single day, that we as a fragile and a deeply divided global civilization continue to exist. So let us now, with all our hard-won modern scientific knowledge, and with our newfound and deeply humbling sense of cosmic perspective, perform the grim, the sober, and the final multiplication. We have our 7 distinct variables, each one a great and formidable filter of cosmic probability. Let us run the full equation twice, once with a spirit of cautious, of tempered, and of scientifically defensible optimism, and once with a spirit of equally defensible, sober, and perhaps more realistic pessimism. For the optimistic scenario, let us make the hopeful assumption that the great biological and sociological hurdles are difficult but are not in the end insurmountable. Let us assign a reasonably hopeful but not outrageous value of 1 in 100 to the fraction of habitable planets that successfully develop life. Let us say that a further 1 in 100 of those living worlds eventually goes on to produce a detectable technological intelligence, a combined value for Fi and Fc. And let us assume a hopeful, a stable, but not an extravagant average lifetime for a typical technological civilization of 100,000 years L. We begin with our now standard astronomical estimate of 4 billion habitable worlds. We multiply this vast number by our biological probability of 1 in 100, which gives us a still impressive 40 million life-bearing worlds in the Milky Way. We then multiply that number by our intelligence probability of 1 in 100 again, which leaves us with a final count of 4,000 distinct technological civilizations that have arisen at some point in our galaxy's history. To find the number active times now times, we perform the final calculation involving the lifetime. A simplified way to think about this is to compare the civilization's lifetime to the age of the galaxy. With a lifetime of 100,000 years and a galactic age of 10 billion years, we arrive at a final calculated value for n of a modest but a very significant and a deeply hopeful number. A galaxy with a few, perhaps a dozen active and communicative civilizations at any given time. A lonely and a vast cosmos, to be sure, but not an empty one. In this scenario, there should be someone out there to talk to. Now let us run the great and terrible equation again this time, with a more pessimistic, a more cautionary, and perhaps given the silence, a more realistic set of assumptions. Let us assume, as many astrobiologists now suspect, that the initial spontaneous origin of life is a truly, a profoundly, and a miraculously difficult one in a billion event. Let us assume, as the fossil record of our own planet seems to suggest, that the subsequent evolution of a high level of technological intelligence is an equally rare, an equally contingent, and another one in a billion long shot Fi and Fc. And finally, let us assume, based on the dark and cautionary tale of our own brief and violent modern history, that the average lifetime of a typical technological civilization is a brief, a chaotic, a violent, and a tragically short one, 1,000 years L. The numbers, when we plug them into the equation, become instantly and completely devastating. 4 billion potentially habitable worlds multiplied by a 1 in a billion probability of life emerging leaves us with a stark and chilling 0.004 life-bearing worlds in the entire vast expanse of our galaxy. The calculation has already at this early stage completely and utterly failed. The cold, hard logic of the numbers forces us to the inescapable and deeply personal conclusion that we ourselves should not even be here. The final calculated number for n, when the multiplication is complete, becomes a statistical and an existential absurdity, a number so vanishingly, so infinitesimally, so heartbreakingly close to zero that it is functionally indistinguishable from it. It becomes a number like 0.000000001, a number that tells us with the cold, the brutal, and the unforgiving logic of pure mathematics that the emergence of a species exactly like our own is a true and genuine miracle, a fluke of such monumental and staggering improbability that we are, for all intents and for all practical purposes, utterly, completely, and permanently alone in a vast, a silent, and a sterile universe. The vast, the almost infinite, and the deeply unsettling conceptual gap that exists between these two equally plausible final outcomes, the 10,000 potential civilizations of the hopeful optimist and the statistical near impossibility of the sober pessimist, is the true, the enduring, and the powerful legacy of the Drake equation. It demonstrates with a stark, a beautiful, and an unforgiving clarity that our final cosmic status, our ultimate place in the universal hierarchy, hinges entirely and precariously on the true unknown values of a few great and perhaps unknowable variables. The equation is in its final analysis a profound and a deeply personal sensitivity analysis of our own collective existence, and what it reveals with a chilling and an unavoidable precision is that our cosmic loneliness is exquisitely and dangerously sensitive to the incredibly small probability of life to the even smaller probability of intelligence, and most critically and most terrifyingly to the average and perhaps fleeting length of a technological civilization's survival. The great and enduring silence of the universe is the single great and powerful empirical clue that tells us which of these two starkly different scenarios is closer to the truth. The 60-year patient, methodical, and completely fruitless search for any sign, any whisper, any echo of an extraterrestrial intelligence is the hard, the cold, and the unambiguous experimental result that we must now, with a heavy heart and a clear mind, plug back into the hopeful architecture of the equation. The silence we must finally and bravely accept is not a mystery that exists outside of the equation. It is the very thing that the equation was from its very inception built to explain. And the simplest, the most powerful, the most logical, and the most scientifically parsimonious explanation for the perfect, the profound, and the enduring silence of our cosmic neighborhood is that the pessimistic numbers, the small and unforgiving numbers, are the correct ones. The silence is the direct, the observable, and the undeniable sound of the great filters at work. It is the sound of a vast and beautiful galaxy where the spontaneous emergence of life is an almost unheard of miracle, where the subsequent evolution of technological intelligence is an even rarer and more precious miracle still, and where the long-term, stable and peaceful survival of a technological civilization is perhaps a miracle that is functionally and universally impossible. For 6 long and patient decades we have stood on the metaphorical shore of the great cosmic ocean, and we have, with a hopeful and a courageous voice, shouted our presence to the silent starry heavens. We have built magnificent cathedral-like ears of cold steel and of warm silicon instruments of such breathtaking power and of such exquisite subtlety that they can hear the faint, dying whispers of the universe's own birth. The Drake equation in its hopeful youth was our confident and trusted map, our optimistic and rational prediction of the thousands or even the millions of other kindred voices that should have been shouting back at us from across the dark and silent water. But the 60-year and still deepening silence of the cosmos has been the great, the sober, and the empirical rebuttal to that youthful and beautiful optimism. It is the real-world answer to our deeply theoretical and speculative question. The equation in its elegant and honest structure gave us a vast and continuous range of possible answers, from a loud, a joyous, and a crowded cosmic party to a quiet, a lonely, and a solitary vigil. The universe, through our own patient and meticulous observations, has handed us its stark and unambiguous verdict. The verdict is silence. The true empirical value of n appears to be, for all of our practical and scientific purposes, 1, and we, in all our beautiful, fragile, and deeply troubled glory, are it. This does not mean, however, that the Drake equation has failed us. On the contrary, it has succeeded perhaps far too well for our own psychological comfort. It has succeeded brilliantly in its primary, its stated, and its most humble task, which was to logically and systematically frame the great problem, to clearly and precisely identify the critical scientific uncertainties, and to rationally and effectively guide our ongoing search for answers. And in the very process of doing so, it has allowed us, with a new and a powerful confidence, to use the silence itself as a potent and a revealing scientific tool. The simple, hard, and now statistically significant fact that we have patiently and systematically scanned the million nearest stars, the stars that are our closest and most likely neighbors, and have found nothing, absolutely nothing, tells us something profound, something powerful, and something deeply sobering about the unknown variables in the equation. It tells us with a mathematical force that is almost impossible to ignore that the final multiplicative product of FL, FI, FC, and L must be an astonishingly and almost vanishingly and a heartbreakingly small number. The great filters of the cosmos are not just a clever, theoretical, or a philosophical possibility. The 60-year silence is our first, our best, and our most direct piece of observational evidence that they are real, that they are powerful, and that they are brutally, almost perfectly efficient. The beautiful, empty, star-dusted night sky is a vast and silent crime scene, and the Drake equation is the brilliant forensic tool that allows us to deduce the terrible nature of the crime, a great, a silent, and a cosmic genocide, repeated 1 billion times over on 1 billion different worlds, with the silent, unseen victims being the almost infinite and beautiful potential for intelligent conscious life itself. So where in this long and perilous cosmic journey does the great and terrible filter lie? Is it in the fiendishly complex and perhaps miraculous chemistry of abiogenesis? Is it in the chaotic, the bloody, and the deeply contingent lottery of biological evolution? Or is it as Enrico Fermi himself, the man who had seen the terrible fire of the atom unleashed, likely and darkly suspected in the final the terrible and the all-too-human variable of L? The Great Silence does not tell us for certain, but it does allow us with a new and a sober clarity to weigh the grim probabilities. Many, if not most, astrobiologists today find it increasingly hard and statistically untenable to believe that the simple emergence of life itself is the one great and final barrier. The fundamental chemistry seems too robust, too universal, and the sheer number of potential habitable petri dishes in the galaxy seems far too numerous. This leaves the later and far more troubling filters, the filters of high intelligence and of long-term civilizational survival, as the most likely and the most plausible culprits for the silence we observe. The galaxy may in fact be teeming with simple microbial life, a vast and silent cosmic ocean of bacteria and algae. It may even be filled with complex life, 1 billion worlds locked in their own unique and silent version of the Mesozoic era. It may be a galaxy of microbes and of dinosaurs, a galaxy where the single great and almost impossible trick is the final strange leap to technological self-awareness. Or, and this is the darkest and perhaps the most likely conclusion of all, it may be a galaxy where intelligence itself arises frequently and robustly, but where it universally, inevitably, and very, very quickly leads to its own tragic and permanent self-destruction. The great cosmic silence is the sound of 1,000, of 1,000,000, of 1,000,000,000 brilliant civilizations that reached their own troubled and perilous version of the 1950s, and who then, one by one, failed to successfully and wisely navigate the perilous and narrow path beyond. The Drake equation in the final, sober and humbling analysis is not a formula that has been exposed by modern science as a failure. It has been exposed with a startling and an uncomfortable clarity as a mirror. Its 7 distinct and sequential variables are not just abstract, distant and impersonal cosmic probabilities. They are in a very real and a very deep sense, a precise and a powerful reflection of our own unique and deeply contingent story, of our own long and perilous past, and of our own deeply, deeply uncertain future. We, the human species, are the living, the breathing, and the improbable embodiment of the first 6 of those 7 variables, having successfully, and against all of the astronomical odds, resolved in our favor. We are the direct and undeniable product of the right kind of star, orbiting in the right part of the galaxy, with the right kind of planet in the right kind of orbit. A planet where life somehow miraculously arose, where intelligence somehow improbably evolved, and where technology somehow dangerously was developed. We have, through a combination of pure luck and sheer tenacity, successfully and blindly passed through all of the great cosmic gates, up to the very, very last one. We are standing right now as a global civilization at the very threshold of the final, the most difficult and by far the most dangerous variable of all. We are the ones in this very century who are in the very process of determining the final numerical value of L for our own unique and precious civilization. The great and terrible question that the Drake equation leaves us with is not about them. It is the most important, the most urgent, and the most deeply personal question that we as a species will ever face. Are we, in the end, the great exception to the great silent rule? Are we the one species in the entire 13 billion year history of our home galaxy that will finally, and against all the odds, solve the paradox in a hopeful and a positive way? The equation does not and cannot give us the final answer. It only, and with a stark and a beautiful clarity, defines the monumental and existential stakes of our current global game. It tells us that the universe is vast, is beautiful, and is filled with an almost infinite potential for life, but that the path to a long, a stable, and a wise future is a razor's edge of almost impossible thinness, with a vast and silent graveyard of failed and forgotten civilizations stretching out on either side. The 60-year and still unbroken silence of the cosmos is not a cause for a deep and a final despair. It is, if we are brave enough to hear it, a powerful and an urgent call to action. It is the universe's own subtle and perhaps final way of telling us that our future is not pre-written in the stars, that our long-term survival is not by any means guaranteed, and that the final, the most important, and the only truly meaningful variable in the entire grand and cosmic equation is the one single variable that is still, for a brief and a precious moment, left for us to solve. Our collective choices, our shared wisdom, our difficult-to-achieve foresight, and our fragile and often failing ability to overcome our own worst and most primitive instincts, these are the things that will, in the end, and perhaps very soon, ultimately determine whether we are just another fleeting and insignificant term in a great cosmic formula that always and tragically resolves to zero, or whether we are in fact the ones who finally, and against all the silent and terrible odds of the universe, become a number that is gloriously, miraculously, and beautifully greater than one.